Hello, we are Team Bomb, and this is a humidifier. A humidifier works to increase the relative humidity in an indoor space when the air is too dry for comfort, health, or even to protect certain materials like wooden furniture. This is an ultrasonic humidifier, meaning that it adds moisture to the air through high-frequency vibrations that break the water into tiny droplets that are then blown upwards, out, and into the air. A humidifier like this contains all three fundamental fluid machines: containers, pipes, and airfoils.
This is a schematic of the humidifier. Water flows from the tank, through the filter, through this pipe, through a heater, and into a water reservoir, where the ultrasonic speaker vibrates the water into little droplets, which are then pushed through the outlet by a radial flow impeller.
The user fills a container, the tank, with water, establishing a hydrostatic pressure variation governed by the hydrostatic equation. At the bottom of the tank, this results in a maximum pressure difference of 2,354 pascals.
If we follow the fluid along its path, it exits the main tank and passes through a water filter and then enters a small pipe that leads to a second reservoir where the fluid is vibrated and released from the humidifier. Flow through the system is driven by the height difference between the tank reservoir and the exit reservoir, which creates a pressure difference in the fluid. Using the known height difference and assuming inviscid steady incompressible flow, the fluid velocity in the connecting pipe can be found from Bernoulli's equation, giving a speed of 1.86 meters per second. If the humidifier's hot steam mode is active, a heater warms the fluid at this stage. Because the fluid column's height differs, the hydrostatic equation predicts a pressure difference between the two ends of the pipe. The system doesn't flow until the column heights reach equilibrium because at the base of the water filter there is a float valve that limits the back pressure. So if the downstream pressure gets too high, it closes and prevents the further flow. This ensures the exit reservoir always maintains the same water level and the fluid will always flow in the correct direction.
Bernoulli's equation assumes inviscid flow, so it overestimates the speed of the water moving through the tube. In reality, friction inside the pipe causes viscous losses and reduces the fluid's energy, thus lowering its velocity. By applying the Darcy-Weisbach equation to account for this loss and assuming a smooth pipe, we predict a more accurate flow speed of about 1.74 meters per second, slightly below the inviscid estimate. There is still some error in this value, however, as the model breaks down for shorter pipes like this.
At the end of the pipe is the exit reservoir. Here, a speaker vibrates at a high frequency to drive capillary waves on the surface of the water. These waves become unstable, creating tiny droplets at their peaks. These water droplets are carried out of the system as mist that adds moisture to the air. The frequency of the speaker can vary depending on how many waves are desired, as long as the frequency of the speaker generates a strong standing wave. Given the application of the humidifier, it is likely that the speaker operates at a frequency ranging from 1 to 3 megahertz. If the frequency were lower, then there would be less droplets and they would be less fine. If the frequency were higher, there would be more droplets and a more fine mist. A higher frequency requires more power, and for the application of this humidifier, perfect atomization of the water droplets is not required. Very high frequencies with high power inputs would likely be used for precise lab experiments or for mixing fluids with ranging viscosities and densities.
The atomized water droplets formed in the humidifier have a diameter of about 5 microns and exit through an outlet into the air. To understand how these water droplets exit, we must first look at how the fan works. Located inside the humidifier is a radial flow turbo machine, also called a centrifugal blower. Each of the 32 curved vanes on this fan act as an airfoil, redirecting air from inside the fan outwards. By taking a slow motion video of the fan under operation and counting the frames per revolution, we found that the fan spins at 1800 RPM in steady state. This represents an airfoil tip velocity of 3.76 meters per second, calculated using approximated fan radius. Assuming a flow coefficient of 0.25, which is typical for a centrifugal blower of this scale, we obtain a radial wind speed of 0.94 meters per second.
Using this wind speed, we can calculate the forces on the water droplet and find whether it will rise out of the humidifier. Since surface tension forces dominate at the scale of a few microns, we'll assume that the water droplet is a perfectly smooth sphere. The Reynolds number of airflow over the water droplet is around 0.318 at standard sea level conditions, which is in the Stokes creeping flow regime. Applying Stokes' law, we find the coefficient of drag over the droplet to be around 75. This yields a drag force on the order of a few nanonewtons. Since this drag force is much higher than the weight of the water droplet, which is on the order of a few piconewtons, the water droplet will accelerate upwards out of the humidifier. An important thing to note is that this calculation breaks down when analyzing the larger droplets of water. Surface tension forces won't dominate, so the spherical raindrop approximation becomes less accurate, and the Reynolds number will increase proportional to the scale of the raindrop, so the flow will dominate from the Stokes' creeping flow approximation.